Welcome, Mr. Sutton here, bringing you the AB Calculus 2-6 Extra Practice Number 4 solutions on continuity. For this problem, we want intervals of continuity for this graph. This graph looks to be continuous everywhere. There's no holes or breaks, so that means our interval of continuity is everything, so from negative to positive infinity. To find intervals of continuity on this graph, let's first identify discontinuities. So we have an infinite discontinuity at x equals -6 and x equals -2. So we're just going to build our intervals around those trouble spots. We have one from negative infinity to -6, union -6 to -2, union -2 to positive infinity, because this goes forever. For this problem, we're finding intervals of continuity for this graph. Let's start by finding the trouble spots. There's only one trouble spot here, and that's at 5, x equals 5, we have a removable discontinuity. So that means our intervals are going to be from negative infinity to 5, and from 5 onward to positive infinity. For this problem, we're finding intervals of continuity for this graph. Let's start by identifying trouble spots. We have a jump at x equals -2. We also have an infinite discontinuity, an asymptote, at x equals 2. And that looks like it. So we have an interval from negative infinity to -2, from -2 to +2, and then from +2 to positive infinity. Identifying points of discontinuity and their type for this problem, this one's actually pretty straightforward. This is a polynomial, which is known to be continuous everywhere, so it has no discontinuities, and we don't have to show any more than the fact that it's a polynomial. For this problem, we're trying to find discontinuities and what type they are. Since this is a rational function, we're on the lookout for holes and asymptotes. I have an x plus 2 in the denominator. If I turn x into -2, I'm going to be dividing by 0. Since I can't get rid of that factor down there, this is going to be an infinite discontinuity at x equals -2. For this problem, we're trying to find points of discontinuity and their type. So this is a radical function, and we know that we can't take square roots of negative numbers. So this function has an undefined area where 2x plus 3 is less than 0. Well, solving for x in this situation, we subtract 3, divide by 2, so we can say we're undefined if x is less than -3/2. To find points and types of discontinuities on this problem, let's take note of what type of function we're dealing with. This is a rational function, which means that holes and asymptotes are the two we're likely to encounter here. To figure out what we have, let's factor the denominator. So we've got an x that we can pull out of here, leaving us with x minus 1 inside. And I see here that these x's are going to cancel out, so that would give me a removable discontinuity at x equals 0. And then this x minus 1 is not going to go away, so we have an infinite discontinuity then at x equals 1. On this problem, I'm trying to figure out if this function is continuous at x equals 3. So let me test my left and right limits and the function value to see if they match up. Left side limit as x approaches 3. That's going to be using this first rule here. So that's going to be 2 over 3 minus 1. 2 over 2 is going to be 1. For the right side limit, as we use this rule that we're approaching from the right with x greater than 3, we're going to have 3 times 3, which is 9, minus 8 gives me 1. And then finally, f of 3, that's going to be using the first rule again, because x is exactly 3 for this one. So that's again going to be 1, it's the same as the left side limit. Since our limit at 3 matches our function value at 3, that means that this function is continuous at x equals, there we go, x equals 3. On this problem, we want to know if our function is continuous at x equals -1. So this is kind of a weird piecewise function. We have this rule here, 1 minus x squared, if x is anything except for -1. And we could say the function spits out 2 if x is exactly -1. So another way of thinking about this is you've got a rule for 1 minus x squared if x is less than -1, and this is actually the same rule if x is greater than -1. That's another way of saying x does not equal -1. Either way, our two-sided limit that we're approaching from the left and the right, if x is anything except -1, we're just approaching using this rule. if we're approaching negative 1. It's going to just be this with negative 1 plugged in, so 1 minus negative 1 squared. Negative 1 squared is positive 1, but you're subtracting it from 1, so that's overall going to be 0. And now the function value, f of exactly negative 1, has a value of 2. The rule right here says so. Since our function value right here and our limit don't match up, we would say that this function is not continuous at x equals negative 1. On this problem, I'm given the function f here, this big piecewise function, and I want to know what c value, and here's your c value, it's this mystery constant. I want to know what value of c makes this thing continuous at x equals 3. And one thing it is important to note is that choice D, there's an option for no such c value existing. So we're going to have to be extra rigorous on this one, can't really take any shortcuts. All right, so let's start by trying to prove that this thing is continuous, and we'll just leave c around until we can actually figure out what it is. So for continuity, I need the limit to exist, the function value to exist, and the two things to equal each other. For my limit, let me start with taking the left side limit as x approaches 3. So to do that, I plug 3 into this left side rule, the x less than 3 rule. So I've got c plus 3c minus 3 squared. And let's see, I can combine those to get 4c minus 9, which I can't really do anything else with at this point. Next, let me take the right side limit. So I'm going to plug 3 now into this bottom rule down here, just plugging 3 in for x in that fraction. So this is just going to be 2c plus, let's see, that's just 3 over 1, so 3. And now, for the limit to exist, these two things have to equal each other, the left and the right limit. So let's set them equal. I can solve this. Subtracting 2c, I've got 2c on the left side. Adding 9 over here, I've got 12 on the right side. So that means I have a c value of 6. And of course, there's an answer choice right here for c equals 6. However, since we're talking about continuity and not just the limit existing, we also have to make sure that this value, or the value that we get when we plug 6 into this limit, we have to make sure that value matches up with the function value at x equals 3. So what is the actual limit of this function at x equals 3? Well, to find that, we just plug 6 in for c in either of these two equations. I'm just going to use this 2c plus 3 one, but they should both give you the same thing. So 2c plus 3, if c is 6, that's going to be, let's see, 12 plus 3 is 15. So 15 is the limit of our function as x approaches 3. Okay, so what's the function value then? Well, f of 3, that uses this middle rule when x is exactly 3. That is a value of 7. Now here's the problem. 7 and 15 are not the same thing. The limit at 3 and the function value at 3 do not equal each other. Therefore, that means this function is not continuous for the c value we found. And since this was the only c value that would even make the limit exist, that means there is no c value that's going to make this function continuous. So that ends up being choice D. For this problem, we're given this rational function here with this mystery a constant in the denominator. And we want to know for what positive values of a, and this is the key here, this f is going to be continuous for all real numbers. So the only way for this thing to have any discontinuities is if we have a 0 in the denominator. So we're going to have discontinuities specifically where x squared minus a equals 0. Well, let's solve and see what x would have to be to make this thing discontinuous. If we add a over here and square root, we see that if x equals the square root of whatever this a value is, then when you square it and subtract a, you're going to get 0 in the denominator. Now, the million-dollar question is it possible to do this for every possible a value that I could pick? Well, it is if a is positive, which is what they said here. If a is a positive number, then we can always take the square root of it and come up with some number that we can then square and subtract a from to get 0. So since a is positive, and we can always square root to find an x value for which a is not continuous, that means that this is not going to work for any positive values of a. So a, or choice A, none is the best answer here. And if you wanted to, you could use process of elimination, right? If we let a be 1, well, then we just have to square 1 and subtract 1, and we've got 0 in the denominator. If a has a value of 2, then you let x equal the square root of 2, and that zeroes out the denominator. If it's 4, well, then we just use 2 for the x value, and that blows that one out of the water. So really, nothing is going to work on this.